All right, aside from alpha decay and beta decay, there are a couple other nuclear changes we need to cover, okay, including gamma decay, which is a release of energy rather than matter, fission, and fusion, which are two processes that have to do with whether atoms break apart or combine with each other. Okay, so usually it requires a little bit more intention on our part rather than just letting something radioactive do its own thing, at least the way we use them and look at them. Okay, so first up, Yemen Decay, right, is again about energy. We have some big excited isotope. All right, excited just means that it's got extra energy in the nucleus, and it's got to get rid of that. So it releases that energy as a gamma ray. Now, a gamma ray, just like microwaves and X-rays, radio waves, and all that, are all just forms of invisible light. We usually don't think of light unless it's the visible kind. It's the white light coming out of your light bulbs at home, or red and green and blue, specifically lights, are coming out of a laser pointer or something like that. But really, light has to do with any kind of electromagnetic wave that we'll get into kind of later on. So gamma rays are just a very high energy version of invisible light. And because it's so high energy, these are actually the most dangerous kinds. Classic comic book characters sometimes get superpowers from gamma rays, but real human beings just get cancer, so I would avoid that at all costs. Now, because gamma rays are essentially just light, they have no mass, okay? There's no protons, no neutrons in here, no nothing. It's just energy. It's just electromagnetic radiation. So when we write a gamma ray in a nuclear reaction equation, we want to make sure that we account for that, in the fact that it has no protons or neutrons, its mass number is 0, and its atomic number is 0. So whenever something goes through gamma decay, we essentially get one of the easiest nuclear equations ever, where nothing changes except it's no longer an excited isotope. We typically show this by using an asterisk like this, okay, to show that our isotope is excited. So, for instance, we might have an isotope of, like, say, cesium. CS. Maybe it's cesium-137. I don't remember what cesium's atomic number is off the top of my head. I think it's 55, but I'm not going to write it just in case I'm wrong. But to show it's excited, we'll have a little asterisk up here to kind of say, ooh, this is excited. It's got extra energy that we need to shake off of this nucleus. Okay, so when you see an asterisk like this, that's a big sign that this is going to go through gamma decay. It's going to release a gamma ray in order to stabilize. Okay, so on the other side of the reaction arrow, this cesium-137, okay, will no longer have the asterisk. Sometimes there will be a little apostrophe or kind of like a something hanging there to show that's a little bit different, but really this is all that matters. It's now just cesium-137 without that little asterisk. Now, of course, we do also account for the energy that comes off of this. So let me see if I can erase this and put this somewhere kind of better. Get my pen back out. So after the arrow, we would have our cesium, okay, no longer excited, okay, and the energy that has been spit out of the nucleus is shown by a gamma ray like this. Okay, and in this case, we do use the Greek letter. Unlike an alpha particle or a beta particle, which are kind of hiding the true meaning of what they're made of, a gamma ray is just a gamma ray. It's just light, and there's not really a better way for it than to just use the Greek letter that we already have for it. Okay, so that's gamma radiation. The mass number stays the same, atomic number stays the same. The only thing that changes is it's no longer an excited isotope, so we drop that asterisk up front. Okay. Next up is fission. Fission is where we have something huge. It's an incredibly massive isotope, usually with a mass number above 200. We break it apart by hitting it with a high-energy neutron, and we end up splitting that large isotope into smaller isotopes. Okay, kind of like what is shown in this picture here. So we throw in a neutron. It breaks this nucleus. Okay, it's fissionable, which means it can go through fission. So we break it. okay, into two smaller isotopes. Sometimes they're similar in size, sometimes one's a little bit bigger than the other, but in any case, we break it apart. Okay, we smash this nucleus into two separate pieces. Okay, typically we also wind up with a couple extra neutrons that fly out of here. So not just these two isotopes that are kind of left from the bigger one, but also these extra neutrons. Either 2 neutrons or 3 neutrons is usually what we see. The reason why we use fission for nuclear energy is because these extra neutrons basically act like that initial neutron we threw in at the first nucleus, where it can go and slam into a new fissionable nucleus to break that apart, which can then go and hit another fissionable nucleus with the extra neutrons that come off of it, and it goes on and on and on. So we start with just one or so extra neutron, and bam, splits it apart. And then that starts to throw out extra neutrons that hits everything else. It makes a chain reaction. Okay, so we don't have to do much to keep the reaction going. Right? Now, when we get these separate nuclei here, these separate isotopes are going to be written just like any other isotope we have dealt with. So kind of think of it like how we keep track of the mass number and the atomic number for alpha and beta decay. Works basically the same way. We're not going to have to worry about trying to, do we call this something specific and new and give it a different name because this came from fission? No, it's just another isotope that happens to be a little bit more stable and is now smaller than the bigger isotope that it broke off from. Okay, so we'll wind up with two separate isotopes, okay, that are just named and kind of figured out just like any other nuclear reaction product, where we have some mass number, some atomic number, and that atomic number comes from, tells us what's on the periodic table, which element it is. Okay, and it just so happens to be that we throw in one neutron on the left, and we have a couple extra neutrons on the right that come out. These are a little bit harder to kind of balance out and deal with because of the extra neutron on the left, okay, and the extra neutrons on the right. So do not forget about these when you are checking your mass number, kind of making sure it's equal on the left and the right. Okay, if you have 2 neutrons on the left, okay, that each have a mass number of 1, that counts for a mass number of 2. You have 3 neutrons, that's counting for a mass number of 3. So watch out for that. Be careful. A lot of the mistakes I see on fission problems come from that, where you see the one neutron's like, okay, that's a mass number of 1, but we don't take into account that there are multiple here. So you got to be careful of that. Okay? So that's fission. Finally, fusion is kind of like the opposite of fission in a couple ways. Instead of dealing with something very, very big, we've got something very, very small. We've got absolutely tiny isotopes, usually with a mass number less than 50, but often even more than that, like way much smaller. Okay, so in this case, we've got 2 versions of hydrogen smashing together. We've got deuterium, which is hydrogen 2, and tritium, which is hydrogen 3. They're just 2 different isotopes of hydrogen, okay, that come together to form a new larger isotope. Now, sometimes we end up with an extra neutron kind of flying off in the process, but unlike fission, we don't need a neutron to start this process. We just need 2 things to smash into each other and combine into one new isotope. Okay? And just like in fission, we do write this as just a regular new isotope. We don't have to worry about saying, but this comes from fusion, so do we give it a new name? No. Okay, again, it's just got a number of protons and neutrons smashed together. What element does that become, and what mass number does it have now? Okay, again, watch out for the mass number of 1 for your neutron that might pop out on the other side. So that way you can get the right mass number and atomic number for the isotope that ends up coming out. Okay? So fusion, rather than taking one large thing and breaking it apart into 2 smaller things, takes 2 very small things and smooshes them together into one new thing. Okay, that's a little bit bigger. And we release some energy and sometimes a neutron in the process. Not every time, but sometimes. Okay, so that's the basics of gamma decay, fission, and fusion. And again, the reaction equations work basically the same way that alpha decay and beta decay works. We just have to know kind of the tips and tricks for these specific nuclear processes so we can recognize them and figure out what's missing in the reaction equation.